I'm going to talk about reorganization energy, engineering in natural systems, and it all grows out of Rudy Marcus's theory from the 50s. You came in at just the right time. And it picks up from his third or fourth slide of his own talk this week. So the people who have done this work, I started it with Fabrice in Paris during a sabbatical. Zhenyu Zhao did all the computation. He was instantly picked up by Microsoft. He didn't even apply for a job. Unique. Bill Rutherford's coming in from the side, and Chris Moser, who was a graduate student of mine in the 80s, is still with me, and we are still friends.
Does that mean you don't give him a good reference enough to move on, or what?
No, he's too well adjusted.
Oh.
So, okay. So I'm asking whether in natural systems, reorganization energy, which is fundamental to electron tunneling, I'll get into it, is adapted for performance. Is it changed from one reaction to another, or is it just adopted? Is it just there? So I'm picking my courage for this work up from a quote from a line of Bob Dylan's. I'm going to gather information about reorganization energy across the entire field of reaction centers. And I'm trying to make it into looking to see if they can coincide for function. And then we'll decide what we can say about it. We are trying to make these proteins ourselves from scratch. I'm not going to talk about that, but we do need to know more about the reorganization energy of natural systems in order to reproduce them in homemade proteins that now are the size, length of photosystem 2. That's the end of that. And there are, by the way, crystal structures just being deposited in the PDB system from our homemade proteins. I put this up here because when we flash activate these proteins, they're terrible. Low quantum yield, not much energetic return. So I'm going to look at all the photosystems that we are all very familiar with, and picking from plants and bacteria spanning 400 millivolts of input energy. We're starting cryptochromes too, but not today. Here they are. We have structures. And we should remember that they do live in membranes. Most of the people who study them forget that. They're in detergent with loss, in my view. So they are involved in reductions and oxidations, we know that. And they also operate across the membrane. People forget that too, with a steady state membrane potential, or delta mu H, of 200 millivolts or so. And I'm going to talk about that as well. We need to consider all these things. So just to let you know, of these systems, only half of them are visibly working, and that's what I'll focus on. So, and just to remind you, there are 3 chlorines and a quinone in the central part of every reaction center. They have separate electron photochemistry. There is a curved architecture, which I'm not going to go into. Light-activated events are connected by multi-step forward reactions, back reactions, and direct charge to the ground. And the quantum yield is near unity. Standard free energy conversion is higher than anything made in the laboratory, as far as I know, and anything that's been made by man, including myself, not practical at this point. The process is quantized in the electron tunneling department, and also the nuclear reorganizations are also coupled to electron transfer. That's what reorganizes, are quantized, not classical. Insensitive to temperature down to cryogenic temperatures. So this is where our route to quantum engineering starts with Fermi's golden rule and meets Brody's expression early. We modified it to be quantized with Hopfield's work. After 25 years, we have this working expression, okay, which is very simple. You can do it and do sums in your head. So I'm going to focus on this totally and ask, what is lambda doing as far as nature is concerned? So this part of it, we'll just look at this part first. Years ago, 25 years ago, we came out with, yes, 13 orders of magnitude of time change with just 25 angstroms change in distance. And this has stood the test of time, despite many attempts to break it. The key is it confirms the 10 to the 13th number of airing. That starts the equation. The slope of this curve is 0.6. We don't go to 2 decimal figures. And this is the distance. So this is set, and it's used very, very much by the field in general. So it's Eyring's rate constant. It's it's adopted, but it's always there. We can't find anything that isn't pointing to 10 to the 13th. The protein as a barrier for electron tunneling is also unvariable in widely different functions over dimensions of natural and unnatural proteins. And of course, distance is critical, highly adapted, high functional selectivity. We've looked at all kinds of ways to see whether packing density or pathways occur, but it's not influenced by that kind of thing. So the straight line, or log straight line, still stands. Nature, to get a long way, just simply crams cofactors together, and in any one group it linearizes distance instead of exponential fall-off. So this is just the background for that. We know it, and I think it's pretty well established. What I'm going to look at is this part, the Rudy part. And here are a set of curves with the Marcus maximum as a just showing lambda, the free energy rate plots as a function of environment, essentially. The more polar the medium, the larger the lambda value. These are the values at the top. So what we've found so far, this 3.1 prefactor is a collected set of constants, including the h bar omega of 550 wave numbers or so, adopted and probably not varied. The free energy, of course, is critical, high functional involvement with selectivity, critical for efficiency. The lambda, having looked at the field over the last couple of years, we know it's a medium for tunneling coupled reorganizations in photosynthetic reaction center superfile family altogether. But we do not know how it's manipulated by nature. Is it low at the beginning of charge separation and then get higher? We don't know. That's what I'm going to look at today. So here's just something from John Miller and Kloss, who introduces to 2 parts of lambda, which is what Rudy did in the 50s and 60s. There's a lambda in, which may be the cofactors, and a lambda out for solvent. And here, solvent is changed, and lambda out gets bigger and bigger and bigger. Well, smaller and smaller and smaller as you go to more and more non-polar media. So for us, for natural systems, we've endeavored to change the free energy to get these curves. I should just remind you, it's free energy versus log rate that produces this parabola. So replaced with a quinone with other quinones, just as I showed in that figure there, we know enough then to alter the free energy between the pheophyton and the quinone. The distance is fixed, hard work to make sure any replacement keeps the distance the same. Delta G values varied, rate constant measured, determine lambda. And Marilyn Gunner in the 80s produced these curves for this changing quinone A and measuring this rate from 113 to 5K. Tunneling, no change in the width of the Marcus curve linked to h bar omega of 70 millivolts or so. What this shows, not much change, and a lambda of 0.7 EVs. Here's a much faster rate she did with the same system. More complicated, more noise, but nevertheless a lambda of 0.6 to 0.7 EVs. So we can look at all the ones that have been determined in spheroides. These numbers are shown here. These have been estimated or measured as I've just shown you. And these, as a function of their natural tunneling rate, are presented versus the lambda that have been measured. And this is spheroides. Here's a similar work with Viridis, Hartmut Mikkel and Paul Matus's work. They independently, nothing to do with us, measured the lambda for cytochrome C to P, to chlorophyll, 0.6. These are the collected lambdas from there. PS1, there's some recent work by Makita and Gary Hastings. Phenomenal clarity of fit on a Marcus curve at 77K and at room temperature, similar numbers in the inverted region, which is what they were looking at for. And that's here in PS1, A1A, and 0.6, 0.58, 0.66. So then a lot of other work from this collection of people, Brettel, Heathcote, Coleman, and Semenoff and Shuvalov have done these, measuring, estimating, calculating the early rates of charge separation in PS1. So let's look at that. Here they go. You can hardly see them, but very pale blue, fitting along the same curve. This is now one from Alan Busak, who's in the audience, I see. A beautiful work, a long projection, but nevertheless, we never talked to him about it. Lambda in this range, 0.5, 0.65. So if we look at, and I should tell you that this is a very long rate and a very slow reaction, milliseconds, hundreds of milliseconds, 1 to 200 milliseconds. And that data fits here. Oh, yeah. So here's Alan's point at 170 milliseconds. But what you can see here is we're looking at 10, 12 orders of magnitude now of time, and lambda is not changing very much. There might be noise in it, but nevertheless, here's a nice flat line grouping them together. This is a phenomenal statement that there is an initial step up from picoseconds to from 0.2 to 0.65 typically. And we think this is a Debye transition. It's very tight, and so early well, let me just show you. So this is just the math. You can talk to me later about it. It's classical. It's 1913, and we are just using his analysis. So for the first, in picosecond time, there's this optical lambda, 0.19. Then it grows to 0.65. He called it static. Rudy called it lambda O or lambda I. The point is, this describes up to here an enormous constancy. The field is full of examples from theorists who are showing in time there's ever more reorganization of the protein because it's multiple time scales of change due to the electron tunneling event. This we totally disagree with here. So what we're looking at is a plot here of lambda versus time. Now we can have a look at something that's more to Marcus's history, free energy versus the rate relative to this parabola. There are two parabolas, as I've shown you, and what we can look at this is how all these data fit on a Marcus plot. So this is spheroides. This is Viridis added, PS1 added, and PS2 added. And you can just see it. But the bottom line of this is this plot accommodates reactions that go over this 12 orders of magnitude of time. They're reactions that go over variable distances of variable times. Some of them are charge separating across a membrane. Some of them are collapsing the membrane potential. And they come from 4 different species. And it's a phenomenal statement of constancy of lambda. So what I'm looking at here then is summarizing back to our equation the 2 terms that have constants, unadopted or unselected. Protein distance, crucial, very highly selected by nature. Free energy, very highly selected by nature. Protein as a medium barrier for tunneling. Unadapted for selected functions. It's just a protein polymer that has not been changed to make electrons go faster or slower. So what about the other one, which I pre-showed you here? It's also unadapted. So we think now that this equation can change to this. So it's clumsy because there's 2 lambdas. I'll show you that we've merged them now in the next section. So what we've got here is 2 sides of this expression, and 0.6, protein is a tunneling barrier, unselected, and the protein is a reorganization medium, similar. Protein generally as a barrier or a reacting medium to tunneling, it may as well be jello. So it's, as jello is shown here, it holds fruit. The fruit are different. It might modify the fruit. It certainly will put their distances correct. But overall, the material is just simply something that holds the reaction. So how does it work? So let's go through a series of reactions for spheroides, and I'll just show initially how the 2 lambdas work. So log rate versus free energy. The initial step is to excite chlorophyll, and Airing's 10 to 13th here. Here's a Debye line, and 200 picoseconds lifetime. The first step goes to bacterial chlorophyll here, and that's the Marcus maximus, as we call it, for the distance at maximum. Free energy, I put in 0.06. The first lambda will come in play because this is very fast. So this is a lambda of 0.15. The reaction rate measured is this. And from this model, it's about 3 picoseconds, correct? That's at this time, before the lambda, before Debye's time. The back reaction for this is fabulous, very, very slow, you can't see it. The back reaction is here, very big lambda, very big free energy down here. But before this can happen, of course, the lambda changes to now 0.65, and this very slow reaction becomes 200 picoseconds. And so that's pretty much what you see, 2 to 500 picoseconds. So there's a dynamic, it's only a time-dependent lambda. So the next step's similar. Oh, this is now a fully integrated pairing of the 2 lambdas together. We've just added the non-electron transfer reorganization change from 0.19 to 0.65. And this is now the new Marcus curve, essentially time dependent. So we can look at the next step here, and a similar story occurs. And the 2 lambdas working together give us the seen rate in biology. And then the back reaction here is from a new distance from here, and 80 nanoseconds is what we calculate here, close. And then the others I'll just tell you, it all works. Once you're below the Debye line, you're back to 1 lambda effectively in time. So calculated using everything I've shown you right now, it is similar to the native measured reactions, and they might be approximate, but they're good enough, as I'll show you now. So here is spheroides again. Let's look at the tolerance to change of the lambda. And I'll just focus on the post-Debye lambda, which is the protein. And we have a 0.3 lambda for the first step, but small difference. So this shows the time course of events to generate an oxidized chlorophyll, loss of singlet state, rise of chlorophyll, low, up, back down, QA reduced, very stable, quantum efficiency 97%, engineering efficiency typically 45, and it lasts for 200 milliseconds. Now let's just have a look at how sensitive it is. If we drop the post-Debye lambda to 0.3, very, very non-polar, nothing happens to the quantum efficiency or engineering efficiency. The time scale of the back reactions of the first 2 steps are very, very slow. So this is a very sturdy charge separating machine. So let's just increase it to 0.4. All you see here is the chlorophyll decay and the pheophytin decay speeding up. And then finally, when you get beyond 0.65, it starts to fail. So here's 52 picoseconds coming from here and here. 20. So this is now going up to 0.8. 0.9, this is now quite polar, and essentially it fails. Well, here's a complete smooth picture of it. So the protein used by nature lives on the edge of this failure, but the thing that it has is very fast charge recombination if the forward rate is blocked. And for this reason, I'm sure that this is to do with photoprotection. So we also started looking, using our lambda, at how efficient we can make the photosynthetic reaction center. And it's quite easy. Well, just plugging in the different midpoint changes and free energy steps, fixed structure, optimized energy levels, far more free energy available. So if you work on this system in the lab, you've got 200 millivolts of unused free energy. In other words, it's running free, this protein that we've all been studying for years and years and years. So this is, should have been found out a long time ago, but it isn't. So anyway, enough of that. I'm now going to just end by talking about the effect of this system, which, as I told you, is overpowered. Well, the overpowering is to drive the 200 millivolts across the membrane to create a membrane potential for John's ATPase. Without this, no ATP. So we're thinking that that extra gap that is missed in the resting state is available to generate a transmembrane potential. So this isn't terribly clear, but it does tell you, modeling. We are looking at a protein across a 35 angstrom dielectric with known projected distances between the 4 components. And we switch on the membrane potential and we watch the midpoints, relative midpoints, apparent midpoints change under the field strength. So let's go across it and looking at efficiencies. So as a potential of 0, because it works very well. A potential of 100 millivolts across the membrane, fine. a potential of 200 millivolts, the value quoted as being operative. Now you're seeing some failure. So, and beyond that, 400 millivolts, a lot of failure. So the bottom line is here, talking about coincidence, what I've done is taken you through a walk that's tested a constant value for lambda, and it fits at every stage and describes a reaction center, spheroides. I'd say in energetic terms, engineering terms, I'd say completely. These are blueprints for engineering photosynthetic reaction centers described in a natural system. So accounting for this, we can do it with a membrane potential of 190. It's got an engineering efficiency of 60%. So I think with that, yeah, I can end. So the bottom line is a simple story of collecting data, gathering data, and showing that they converge in a common action. So 0.65 EVs is the lambda to take care of. We're now going on to look more deeply with photosystem 1 and 2, and whether this will continue to confirm a singular lambda, only testing will tell. But it looks like it's showing very well that a single lambda will fit all these systems. Thank you.
Excellent question. We have time for two quick questions. Yeah.
So it would be interesting to see your extension to photosystem 2 because
As you know, photosystem 2 is almost twice as effective as the bacterial reaction center stabilizing the energy of the charge separation. And so, but it does pay a consequence. There's more misses and lower quantum efficiency.
What's the definition of more stable?
Well, so if you take the photon energy and look at how much the redox free energy is in the primary charge separation, it's much higher in photosystem 2.
So that's because the amount of energy expended to separate charge across the membrane is constant, whether it's photosystem 2 or viridis. So the amount used up to separate charge just is the same level of event. You know, it's the same proportion. Well, it's the same amount, different proportion. So, but nevertheless, there are more complications in photosystem 2. And I think we are finding that some of the pathways, particularly of decay, have been misassigned. There's got to be multiple steps. And that's applying his theory also.
Okay, it'll be interesting to see that.
Yeah, well, that's coming.
So I think that there's, from a computational perspective, I think that if we have a fast electron transfer process, we usually try to equilibrate the system only on the timescales that the process happens. And I think that there is a very interesting, if you equilibrate it much longer than it's supposed to happen, you start getting this steady increase of the lambda. So is this consistent basically with your model that the system doesn't fully have time to relax to the other configuration?
Less than 13 picoseconds.
Yes.
Yes, there's no relaxation of the protein at that point.
Yeah.
But, you know, as the data, empirical here, as the data shows, there's a very rapid step to another level. It's not drifting along as theorists are indicating, and their work is only theory. Oh, yeah. It's theory.
Yeah.
So,
Les, in one of your last slides, you showed that the quantum yield seemed to go down quite a lot when you went to 200 millivolts of membrane potential.
right.
Isn't that quite surprising?
No, that's a different quantum yield. The quantum yield is like, it's 90% instead of 97 or 85 it was. So I think the number's wrong that's on there. Is that right? Or are you amazed that it's gone down to 85?
I'm surprised it's gone down to 85.
Okay, so that's the wall that as the membrane potential increases, now the system is underpowered to drive it.
So I suppose I was imagining
it probably runs to a point where it can't go any further.
But have you tried to see if you could redesign the energy levels to keep that up at a higher level under 200 millivolts of potential.
No, that's, so in order to do that, we lifted the midpoints energy levels up to a point which would accommodate. And if you carry on going, then the back reaction starts competing for the forward reaction. So it switches off. So, you know, I just picked 190 because that I should say, that was a number measured and reported in 1968 by Crofts and Jackson. So we just picked that. So, but we can make it continuous and just watch a little more sophisticatedly how it fails.
Two last questions.
At the end, you suggested that when you drive the system at a high membrane, on a high proton-motive force, the system broke down. I didn't follow. Could you elaborate what you meant and how? I think you said that it breaks down. The rules.
Right, because the
So how does the system respond then?
because the fear-fighting midpoint is being pushed up and up and up, and the monomer chlorophyll is up and up and up, it's actually higher than P star. But even before it gets there, the back reaction rates to ground are speeding up. So it's failing because it's simply
The system
matched.
leaks. It leaks at
It's
high
leaking more and more and more.
Yes, you showed us that in all the reaction centers, the lambda is basically the same. So I was wondering, what's the lambda in your maquettes, and if it's different, why it's different?
I don't know, but I can, you know, I can waffle. Okay. One, we've now made an oxygen carrier. You know, it behaves like hemoglobin and myoglobin, very stable. That indicates it doesn't let water in, so it's dry. So we have yet to put a system that we can test lambda in a photosynthetic system already, but we expect it to be, you know, 0.7 maybe or something like that. So interior of our maquettes are dry, and we now have structures to 1.4 angstroms that shows everything very tight. So how close is a 4-helix bundle interior to the water outside? Well, it's not far away, but even lambdas in reaction centers that are close to the surface are still 0.65-ish, you know. So we are expecting it to be possible to make low 0.65 EV lambdas.
So once you have achieved that, you think you have the same efficiency in the maquettes as in reaction centers?
They will be, sorry?
If you then, once you have engineered
yeah.
the lambda the same, it should be the same efficiency?
Yes, we expect it to be the same. And the other thing, we're now modifying our maquette. We're putting 2 chlorophylls close together at the that initiates a charge separation, because I think the sub-Debye lambda is critical for the first steps. It saves a lot of free energy initially, because lambda is very small and you can get to the top of the rate with very small energy use. So that's needed, and then it relaxes to a larger one, and that speeds the back reactions up, but not too badly, good for photochemical stability. So we're now going to add another component to our maquette.
Okay,